In step 5, we compute the test statistic for our chi-square goodness of fit test. And that test statistic is exactly this here. We've got the sum of the squares of the differences in the O and the E's divided by the E's. Again, the O stands for the observed frequencies. Those are the frequencies observed in the survey or the sample, and that are these right here. So you can see I've got the O column already filled out with 570, 432, 282, etc. And then the E column, the expected frequencies, you get those by taking the sample size times the percentages that are expected. And in this case, you've got the percentages right here for the expected distribution of coffee drinkers. So we have to do a computation to get each of these. So first, let's just write one of these down here. We've got E equals the sample size was 1600 times the percentage that goes with this one right here, the 570, that was for 0 cups, is 36%. 36% of 1600 is 576. So the expected amount was 576 that would drink 0 cups out of 1600 people. Then for the next one that goes with the O of 432, we've got the expected value is the sample size 1600 times the 432 goes with 1 cup, and the expected amount is 26%. So we need 26% of 1600, which is 416. And if you continue this computation for each of these rows, we get 304 for this one, we get 144 for this one, and we get 160 for this one. So real quick, before we go on to finishing the computation of the test statistic, this is now what we meant by does the observed fit the expected? If you look at these numbers, they're not exactly the same, but they're not way off by any means. It's not absolutely crazy. Like, for example, if this came out to be 176 is expected and there actually were 570, that'd be a very big difference. So as of now, it doesn't look too crazy, so we might end up being comfortable saying that this is in fact the distribution of cups of coffee. Now, notice we still have computations to do. These are our observed frequencies, these are our expected frequencies, but the test statistic is this computation right here. Chi-squared is this computation. So by the order of operations, we certainly need to do the subtraction first because it's set off in the parentheses. So that's why I've got a row here or a column here for O minus E. We then would need to square that next. So I have a column here for the square of O minus E. We then need to do the division by E. That's why there's a column here for that. And then our final answer will be the sum. We now can complete our computation for the test statistic. As you can see, with the goodness of fit test, the test statistic is a bit laborious in computing. If you had a multinomial distribution with a lot more categories than 5, for example, 10 or 15, you would never do this computation by hand. There are statistical packages that can actually compute the chi-square test statistic for you. But let's finish this one by hand so we know what it is that the statistical packages are doing. So the difference of the O's and the E's, 570 minus 576 is negative 6, 432 minus 416 is 16, 282 minus 304 is negative 22, 152 minus 144 is 8, and 164 minus 160 is 4. We then need the squares of all these. So we've got 36 here, 256 here, 484 here, 64 here, and 16 here. And then finally, we now need to take these values here, this O minus E squared, the square of those things, divided by this column over here, divided by the E's in that order. So 36 divided by 576 is 0.0625. 256 divided by 416 is 0.6154. We continue this, we get 1.5921, 0.4444, and 0.10. To get our test statistic chi-square, our final step is to add all those quotients, which are here in this row. If you take the sum of all those, you get 2.8144. In step 5, we compute the test statistic. We also then make a decision on whether we should reject or fail to reject the null hypothesis based on where this test statistic falls in the graph that we drew in step 4. Let's take a look at that again. Here is the test statistic we just computed, and here is the graph that we came up with in step 4. So to finish step 5, we need to see where this falls. Of course, 2.8144 falls well to the left of 9.488, which is the number that divides the fail to reject region from the rejection region. So we are going to fail to reject the null hypothesis. Step 5 is not only that computation giving us chi-squared, but we also fail to reject the null hypothesis. We are now ready to move on to the 6th and final step. Before we complete step 6, we have a summary here of what we've done so far. In step 1, we've defined our pair of hypotheses. In step 2, we've noted the level of significance. In step 3, we've determined the tail and type of test. In step 4, we've drawn the graph of our probability distribution function, shaded the tail region, and came up with the chi-squared value that separates the fail to reject region from the reject region. Step 5, we did the computation of the test statistic, and we saw that that falls in the fail to reject region, which means you fail to reject the null hypothesis. Finally, in step 6, we need to determine what we should do with the claim itself. Notice I did not write down which one of these is the claim. You don't necessarily need to do that so much for the goodness of fit test or the coming test known as the chi-square test for independence. Instead, just look at it. It says fail to reject the null hypothesis. Here's the null hypothesis. So we're failing to reject that 36% of American adults drink 0 cups, 26% drink 1 cup, 19% drink 2 cups, 9% drink 3 cups, and 10% drink greater than or equal to 4 cups at a 5% level of significance. So let's write this in. At 5% level of significance, we fail to reject And instead of writing this all down again, let's just simply say the way they expected the cups of coffee to be distributed. So at 5% level of significance, we fail to reject the way expected coffee cups to distribute. We've already written it down in H0. It's laborious, so we can save a little time here, as long as we've got it in here at one point. So this is our step 6, and now this is the complete entire problem. When you come across a problem like this is the 6-step process that you would want to go through to answer it. We've now completed a chi-square goodness of fit test.